Our section today is on different kinds of variation. We have direct variation, we have inverse variation, and we have joint variation. Okay, so direct variation is probably the one you're most familiar with. So let's see, and then we'll talk about the other two as we get there. This section's pretty easy. Assume you have a job of shoeing horses. None of the horses are disfigured or physically abnormal. If there are 5 horses, then you need how many horseshoes? 20. How did you get that? 4 legs, right? So 5 times 4 is 20. So if there are 12 horses, how many horseshoes do you need? 48. If there are 25 horses, then you need 100 horseshoes. So as the number of horses increase, the number of horseshoes also increases, right, at a constant rate of 4 each time. So we would say that the number of horseshoes is directly related because as one increases, the other also increases. What about if your number of horses decreased? Then what would happen? Then the number of horseshoes needed would also decrease. Okay, so the formula that we use for direct variation or directly proportional is y equals k times x, where k is some constant. Okay, and if you look at this formula, it looks a lot like our slope-intercept form of an equation, right? There's no plus b at the end, but this is just like y equals mx, where k represents the slope. So in this problem, the k would be 4, because that's what we are increasing by each time. Okay, so our example, it says 12 gallons of golf. Oh, I wish I was playing golf. 12 gallons of gas cost $25.44. How much would 18 gallons of gas cost if the cost of the gas is directly proportional to the number of gallons bought? So because we know this is a direct proportion problem, we know we could set this up as y equals k times x. Now, on these problems, it's easier if you can identify the correct y and the correct x and let that work out. So here's a little tip that will be true 95% of the time. Okay, this is true. If we have money involved, that's going to be equal to the y value. If we have time involved, that's going to be equal to the x value. And that, just knowing that alone will help you, like I said, on 95% of the problems that you'll have to work. So in this one, we have a money value in our first. So our first equation here, we know that y equals kx, and we know we're dealing with 12 gallons costing $25.44. So our k, the thing we don't know, is the price per gallon. So we can find that out by substituting in. So I'm going to let y be equal to the money. So I would say $25.44 is equal to k times x is the number of gallons, which is 12. And now we are going to divide by 12.
It's 212.
Okay, and you, again, think about what this is. This is the price divided by the number of gallons. So it's the price per gallon, which is what we're looking for. Right, when we divide like that. So it's $2.12 for every gallon. Now we're going to take this information, we're going to plug it back into our equation. So now we know K is 212 for any number of gallons. So it becomes Y equals 212 times X. Now we want to know How much would it cost if we got 18 gallons? So again, that is our X value. So we would say Y is equal to 212 times 18. Which gives us a value of $38.16. The cost of a smoothie is directly proportional. So there's the key word. It tells me, hey, this varies directly. It's directly proportional to its size. A 12-ounce smoothie is $3.60. Then what is the cost of a 16-ounce smoothie? So we've got Y equals K times X. We're dealing with money, so I'm going to make the money my Y value. So 360 equals K times X is 12. Now we want to solve for K. So again, we're looking at the price per ounce this time of a smoothie. So 360 divided by 12 would be 30 cents. So it's 30 cents for every ounce. Now we're going to take this information, plug it into our original equation. So we know it's Y equals 0.30 times X. Now we're wanting to apply this when it's a 16-ounce smoothie. So Y equals 0.30 times 16. And that would tell us the price is $4.80. Okay, so as I read this one, the amount of fertilizer needed is directly related. So there's my key word. Because it says direct, I know I'm dealing with a direct proportion problem. Now we're talking about 15 pounds of fertilizer to cover 6 acres. So how many pounds are needed to cover 40 acres? So this time I don't have money and I don't have time. So what I normally do is, I know I'm going to be dividing by X, right? Because I want to get K by itself. So I just normally like to think, well, which one would I rather deal with? Pounds per acres or acres per pound? Well, pounds per acre makes more sense in my head for how you would normally work that problem. Now, you really can't get it wrong if you do it the other way. But because I want to do pounds per acre, I'm going to let pounds be my Y value. So I'm looking at Y equals KX. So that's going to be 15 pounds equals K times 6. I just have to remember which one I let be which value. So I let Y be equal to my pounds. I let X be equal to my acres. Okay, divide by 6. So it's going to tell me K is equal to 2.5. So I'm going to plug that into my original equation for K. So Y equals 2.5 times X. Now we're wanting to apply the situation for 40 acres. So again, acres was my X value, so I'm going to plug in 40 for X. And that's going to give me Y equals 2.5 times 40, which means Y is equal to 100. So I would need 100 pounds for 40 acres. Or inversely proportional. So the way that we set those equations up is Y equals K divided by X. Okay, or another way that you might see this, think about if you cross multiplied. You would get K is equal to X times Y. So you'll see that written in either one of those forms. Okay, so let's look at what kind of problems we're dealing with here. The time required to rake the grounds at Rockwood Manor varies inversely with the number of workers. So if 4 workers can complete the job in 12 hours, how long would it take 6 workers to complete the job? So what do we expect to happen here? If we have more workers, the time it takes us to do the project is going to decrease. So that's why it's inversely proportional. With the direct proportion problems, we had number of horses, and how many horseshoes did we need? Well, that was always increasing. If I have more horses, I need more horseshoes. Now I have more workers, so it's going to take less time. That's what makes it an inverse variation problem. When one number goes up, the other decreases. So we set this up as an inverse proportion. Again, it tells me, keyword in there, inversely. So I know which formula to use. I'm dealing with workers and time. So I'm going to let time be equal to my x value. So when I set this up, 12, the number of workers, 4, which is the number of workers, equals x divided by 12 hours. Okay, then again, we solve and get k by itself. So it tells me k is equal to 48. So the constant of variation this time is 48. So I plug that into my original equation. So now I have y equals 48 over x. Now I want to know what would happen if I had 6 workers. So I'm going to plug 6 in for y. So that tells me 6 is equal to 48 divided by x. Put that over 1, cross multiply. So that tells me 6x equals 48. I divide by 6, which tells me x is equal to 8. So if I had 6 workers, it would only take 8 hours. Whereas 4 workers, it took 12 hours. Okay, the time it takes 6 men to dig a ditch is 20 hours. If the time it takes to dig the ditch is inversely proportional to the number of men, how long would it take 10 men to dig the same ditch? Okay, so again, we're using an inversely proportional setup. So I've got y is equal to k over x. I know I want x to be the amount of time. So in the original setup, 6 people did it in 20 hours. So that would be 6 equals k over 20. I solve for k. That tells me k is equal to 120. So I take that information and I plug it in for k. Now I want to apply it in a different situation. Now what if I had 10 men? So 10 is my y value because time is my x. So 10 equals 120 over x. Put this over 1 and cross multiply. 10x equals 120. Divide by 10, so x is equal to 12. So 6 people, it took 20 hours. 10 people, it'll only take 12 hours. We're going to look at is joint variation. So joint variation is very similar to direct variation, except there are multiple things that are varying directly. Okay, so our normal formula for joint variation is y is equal to k times x times w. So here's an example of a joint variation problem. The cost of constructing a 9 by 12 patio is $734.40. If the cost varies jointly as the length and the width, then what does an 8 by 14 foot patio cost? Because essentially, what are we doing here? Multiplying the length by the width. We're finding the area. So the area we need to cover changes as both the length increases or decreases and the width increases or decreases. So again, it's kind of common sense that you would need both of those to find the cost. So again here, I've got a cost of $734.40. That's going to be my y value. Anytime I have money, I'm going to make that the y value. So $734.40 is equal to k times x. So we'll let x be 9, and we'll let w be 12. So 12 times 9 is 108. So 108k equals $734.40 divide by 108. That tells me K equals 6.8. So I'm going to take that and substitute that in for K in the original. So now I have Y equals 6.8 times X times W. Now we're wanting to do the same with an 8 by 14 patio. So now we do not know the cost, so we'll let that stay Y equals 6.8 times X. So we'll let X be 8 times W. We'll let W be 14. Then we multiply all three of those. We obviously get the value of yeah, I didn't need your help or anything. And that would be a joint variation problem. The weight of a can of baked beans varies jointly with the height of the square of the diameter. If a 4-inch high can with a 3-inch radius weighs 14.4 ounces, then what is the weight of a 5-inch can with a diameter of 6 inches? Okay, so this one we do have to spend a little more time thinking about. So weight varies jointly. So I'm going to say that the weight is equal to K times, and then what are the two things it varies jointly with? The height, so times H, and then the square of the diameter. So that would be the diameter squared. So that's going to be my joint variation equation. Now I've got a 4-inch high can, so 4 would be the height. A 3-inch radius. Okay, so what could that tell me? Well, if the radius is 3 inches, the diameter is 6 inches. And when I plug that in here, I would plug in 6 and then square 6. I know that this is equal to 14.4 ounces. So then 6 squared is 36. 36 times 4, 24, 160, 136. Dang it. 144K. Well, that makes a lot more sense. Equals 14.4. I would divide by 144. Oh, what happened? There it goes. And so that would tell me K is equal to 0.1. Now I would take that information and plug it in to my original. So now I have weight equals 0.1 times height times diameter squared. So in the new situation, I know that the weight is 5 inches. Nope, I do not. What is the weight? So I'm looking for the weight. How can a weight be 5 inches? You idiot. 0.1 times the height. The height is 5 inches times the diameter, which is 6 inches squared. So 36 times 5 is 180. 180 times 0.1 is 18. So the weight would be 18 ounces. Okay, the time required to process a shipment of oysters varies directly with the number of pounds in the shipment and inversely with the number of workers assigned. So now we've got both a direct variation and an inverse variation problem at the same time. So let's use our variables to write this out. So time is normally, but not now. Not now. Because it tells me time to process a shipment varies directly with the number of pounds. So time is equal to K times the weight, but it's inversely with the number of workers. That's great. So what variable do we want to use for workers? We'll do P for people. Okay, so the time required is directly related to the number of pounds, which I used as weight. Boy, I really should. That's bad. Can I change my variables? I'm going to get confused. Okay. So since we're using pounds, let's just make that P over workers. We'll make that W. I just completely swapped them. But that was bad to use people for, let's just pay attention. So 3,000 pounds. So that is the weight, right? 3,000 pounds, that's going in for P, pounds, can be processed by 6 workers, that's going in for W, in 8 hours. I wrote over that. Yes, 8 hours. So that is the amount of time. So we're going to substitute all of those values in to find out what K is. So that would give me 8 is equal to K times 3,000 divided by 6. 3,000 divided by 6 is 500. So 8 equals 500K. I would divide by 500. And that tells me K is equal to 4 over 250, 2 over 125. But y'all probably want to make that a decimal. What is that as a decimal? 2 over 125. 0.016. Okay, so now I know what K is, so I'm going to plug that in to my original and then apply it in a new situation. So let me clean some of this up so I can see the numbers. There we go. So now as I'm plugging in, T equals 0.016 times P over W. Now in the new situation, we want to know how long would it take 5 workers, so 5's going in the denominator, to process 4,000 pounds, that's going in the numerator. So as I plug those values in, 0.016 times 4,000 divided by 5, that would be 640. 640 divided by 5 is 1, 2, 4. That's what y'all got? Yes? All right. 12.4? 12.8. Dang it. I was so close. I was going to say, God, 124 hours? That's not very good time.
I thought we were talking about work still, and I was like, how can you have 12.8 work?
You can get that sometimes. You just have to make it 13.
So they will always be on the high side.
Mm-hmm.